Hey there everybody, this is a video for the 30SH students, and we are going to go through pages 9 to 12 in the Trig booklet. This is going to be a little longer video than the last three. Hopefully you've watched the last three videos. We're going to kind of refer to them and maybe review and summarize them a little bit in the first couple minutes. And this video is going to focus on kind of four questions. Question number one, how can we be expected to do trig with no calculator? An important idea. Question number four, how can we get exact answers in trig? And we'll look at what that means in a minute. And why are sine, cos, and tan called the circular functions in mathematics? I mean, I don't know about you, but the first time I saw sine, cos, and tan, I was trying to find unknown angles and unknown sides in right triangles, and there was no circles involved. And finally, speaking of circles, there's this thing called the unit circle. I bet you've heard about it. I bet you've heard that, oh my word, it's so hard. Grade 11, you got to deal with the unit circle. I'm here to tell you that not only is the unit circle one of the more important things you do in high school math, for those of us who like math, it's one of the most fun. It really is something that ties together so many ideas that you've been learning since grade 7, from coordinate geometry to algebra to trigonometry to circles to triangles. It's just such a cool thing, and I hope I can make you love it at least a little bit as much as I do. So this is what we're going to focus on this video. So this will be a little longer than the last couple. Let me get display capture happening. Display capture, infinity. So then what we're going to start with is our good old YX coordinate system. And the first video I did for trig went through pages 5 and 6. And we learned some very important ideas, such as the idea that angles don't have to stop at 90 degrees. As long as you start at the origin with your vertex, an angle could go, for example, to here, and we would call that, of course, the terminal arm. The initial arm is always, when you're doing basic angles and in trigonometry, the initial arm is always the positive x-axis, which there's the x and there's the x-axis. I'm using a very big piece of paper here for a reason that'll become apparent in a few minutes. So you can see my box of Kleenex propping up my my webcam, so hopefully I don't get all clumsy and knock everything over. So anyway, this might be, I don't know, how big is this? Let's see, let's use a protractor and see how big this is. Remember, your protractor goes past 90. Your protractor has all the way to 180, so that looks like it's about 55 degrees. So, oh, wait a minute, sorry. It's about 55 degrees going from here to here, so it's actually about 125 degrees. So this is a 125 degree angle, and that means that it has a reference angle, and that was kind of the whole point of the first lesson in this chapter. So it has a reference angle this way of 55 degrees, and of course those two things add up to 180, which makes sense because it's 180 degrees along a straight line. So if that makes sense to you, then of course you realize that you can do angles over here as well. You can put an angle. This would have been an angle in quadrant 2. Of course, this is quadrant 1. And let's put an angle in quadrant 3 and see what it looks like. Let's put a blue angle down here. Let's use an actual ruler and make it nice. So something like that. So starting from here, that would be an angle that goes from there to there. And let's see, how big is that angle? Well, this one's going to be a little harder to measure. I'm going to have to use something like a little bit of a trick here. Looks to me like, again, it's pretty close to 55 degrees, maybe a little bit off. Here, let's see. Yeah, about 55 degrees. But that's 55 degrees, again, as a reference angle. So it's a 55 degree reference angle, and the reference angle always goes to the nearest x-axis, but the actual measure of the angle would be 180 plus 55, so that's going to be a 100, and sorry, let me say that again, that is going to be a 235 degree angle. Of course, if I kept going and made an even bigger angle past this line, I'll go back to black, I could have an angle down here in quadrant 4, and that angle in quadrant 4 might be like that, in which case, to get to that angle, I have to go all the way around to here. Okay, this one's not going to be 55 again. That was just coincidence. The two of them turned out to be 55. So I was just trying to do this kind of just off the top of my head here. And that's maybe about 20, looks like it's about 23 degrees as a reference angle. But its actual standard measure would be 360 minus 23 degrees, which would be somewhere along the lines of 300 and, let's see, 60 minus 30 would be 40, so 337 degrees. And there we go. So that's a 337 degree angle, but it's the same place on a coordinate grid, if you put the vertex at 0, 0, as a 23 degree angle would be. And what that means is that even though you learn sine, cos, and tan as just things for right triangles, well, if you go beyond right triangles and start talking about perhaps triangles or situations where you have a 337 degree angle, obviously you couldn't have a 337 degree angle in a triangle, but if you had a situation where you had a 337 degree angle, you could still talk about its sine, its cosine, and its tangent because it has a related reference angle of 23 degrees, and no problem putting 23 degrees in a triangle. It would just be this triangle right here. There it is, triangle. So that's kind of the important idea of lesson 1, that there's 4 quadrants, 1, 2, 3, 4, and you can put all angles that you measure on the quadrant coordinate plane with the vertex at 0, 0, the initial arm as the positive x-axis, the terminal arm wherever the terminal arm ends up landing in quadrants 1, 2, 3, or 4, and if you land in quadrants 2, 3, or 4, you can always find a reference angle that would be acute, that is the angle that's the shortest distance to the x-axis. And because I can always relate any angle to its reference angle that's acute, I can take any angle you want and do trig with it and find sine, cos, and tan. So that was the first thing you learned. So that was basically what lesson 1 was about, or the one we did Thursday, page 5 and 6. So that was what kind of the point of 5 and 6 was. Then we went to page 7, and page 7 was all about a family of angles. And it was the 45 degree family. And I actually don't even remember if I pointed this out in class or not. But you ever notice that your geometry set gives you 2 triangles, and they're special for a reason? This is your 45, 45, 90 triangle. And I can take that triangle and I can put that triangle right here. I'm just going to draw it really kind of rough sketch. And there it is. And we did some Pythagoras on that and found that we know exactly how long each of these lines is. We decided that we're going to make the hypotenuse 1. So 1 unit. I think I actually said 1 meter in the example we did, but it could be 1 centimeter, it could be 1 mile, it could be one whatever you want, 1 unit. And if the hypotenuse is 1 unit, then this side is the square root of 2 over 2, and this side is the square root of 2 over 2. And that means that if this is my theta, I now have some answers for the sine, cos, and tan of 45 degrees. So if theta here is 45 degrees, look what I can do. I can say, and this is where, can you please take out page 9 now, and I can now say that the sine of 45 degrees must be, let's look at the picture again, opposite over hypotenuse. Well, if the hypotenuse is 1, dividing by 1 doesn't mean anything. So it's the square root of 2 over 2. And if you're wondering again where this number came from, go back to video 2 and you'll see exactly where it came from. The cosine, well, it's a 45, 45, 90, so these two sides are the same. This is an isosceles triangle after all. So that would mean that this is adjacent over hypotenuse for cosine, which is still root 2 over 2 divided by 1, which is still root 2 over 2. And tangent is, of course, opposite over adjacent, which is going to be 1. Anything divided by itself is 1. You might want to change these. Again, I like thinking about this hypotenuse as 1. You can think about it as whatever you like. But if this is 1, then this is root 3 over 2, and this is 1/2. And here's the triangle we were just talking about. If this was 1, then this is 1 divided by root 2, 1 divided by root 2. And again, just like we did in the video, we like to put that as root 2 over 2. It's the same number, but it's got no radicals in the denominator, which us math types like a lot. So that was the whole gist of video 2, was that you can have a 45, 45, 90 triangle, and you can know its sine and cosine without touching your calculator, because you know in any triangle that's this size or this shape, basically these ratios will be the same. Think about it. What if I made this triangle twice as big? Well, then this would be 2 times bigger, this would be 2 times bigger, this would be 2 times bigger. But when I did opposite over hypotenuse, those 2's that made it bigger would cancel. If this was 10 times bigger and this was 10 times bigger, well, the 10's would cancel. I'm still going to get root 2 over 2. And your calculator knows that, right? Assuming that you're in degrees when you start punching, the sine of 45 degrees is that number. And again, that's a rounded number, right? One of the questions I put on that front page was, what can we do to find exact answers in trigonometry? Well, that's an estimation, right? I'm stopping at that decimal place. It goes on forever after that. If I take the square root of 3, or sorry, oops, I haven't punched it yet. Square root of 2 divided by 2, I get the same decimal that you just saw a second ago. So the calculator knows that that is root 2 over 2. In fact, fancier calculators will spit out when I do, when I do sine of 45, it'll actually spit out root 2 over 2. In fact, I think I have one of those calculators. Give me a sec. Does this one do that? I think it might. Sine of 45. Oh, no, I guess it doesn't. Oh, wait, am I in degrees? Oh, I'm not in degrees. That's the problem. Okay, how do I get to degrees? I'd like to be in degrees, please. And sine of 45. There it is. I knew this calculator did that. So there it is, root 2 over 2. So now you're probably thinking, oh, great, I got to run out and buy one of these fancy calculators for 40 bucks. No, you don't. All you need to do is understand this thing that we're about to generate, which is called the unit circle. And here's kind of where it comes from. So see this triangle here? I put it there. Well, remember that means that I've put a terminal angle right there. I've put a terminal arm, I should say, right there. What if I put the terminal arm over here? What if I put the triangle over on this side? And we'll do this in our notes in a minute, don't worry. I just wanted to do it on a big piece of paper with the actual triangles from the geometry set, just to kind of make a point and so that it's easy to look at. Okay, now again, that's still a 45-degree angle from here to here, but that's a reference angle. The standard form of that angle is that is, of course, 45 minus from 180, which is 135 degrees. So I can say that once again, all these proportions are still the same. This is still root 2 over 2 for a length. This is still root 3 over 2 for a height, and this is still a hypotenuse of 1. What I can say here is that I can say the same thing for sine, cos, and tan, except one little difference, in that the distance from here to here is root 2 over 2, but because we're on a coordinate plane, and because the x-axis is negative in this direction, I call that a negative distance. And if you're thinking to yourself, oh man, what do you mean a negative distance? I've never thought of distance as being negative before. Maybe it would help you to think about it as the coordinate plane. And why don't you think about it as, in fact, there's coordinates here, right? Think about the coordinate axis. This x value is root 2 over 2. This y value is root 2 over 2. This x value is negative root 2 over 2 because I'm going to the left. And this y value is still positive root 2 over 2 because I'm going up. If I put the same triangle down here, well, now something else changes. Once again, I'm still going to have a 45-degree angle that way. And I'm still going to try my best to draw this as nicely as I can. Can you still see that? Yeah, you can still see that. There we go. There's the triangle, and there's 45 degrees as a reference angle. But this angle now, in standard form, is actually, let's see, 45 plus 180, which is 225 degrees. So I can say that the sine of a 225-degree angle is this opposite line over this hypotenuse. And this opposite line is negative root 2 over 2. And why is it negative? Well, it's negative because y values go down on the y-axis when you go this way. So again, let's put some coordinates on this. This is x is negative root 2 over 2. and y is negative root 2 over 2. Okay, and that's what we found out when we looked at, where did I put the page? When we looked at the 45-degree family right here, we found that when we were at a 225-degree angle, sine was negative and cos was negative. Oh, but tangent was positive. What the heck? Why was tangent positive? Well, tangent was positive because, think about it, tangent is positive because opposite over adjacent is tangent for this angle here, and they're both negative. What's a negative divided by a negative? It's positive. So there we go. And then one more place I can put this triangle. I can put this triangle right here. And let's join it this way. There we go. And that's this triangle right here. And once again, it has a reference angle of 45. Oops, that's the saddest looking 4 ever. Has a reference angle of 45 degrees. 45 degrees from there to there. But again, to get to this arm using standard form, you have to start at the positive x-axis and go all the way around. Boop. And that would be, of course, then 360 minus 45, which is 315 degrees. So this is a 315 degree angle. But notice that all the numbers are still the same. This coordinate here, it's still the same height as this, so it's still negative root 2 over 2 for y. And it's still the same x distance as that, so it's root 2 over 2 for x. So if anybody has told you, oh man, this unit circle thing's hard to memorize, it's really not if you just understand where the triangles are sitting. Now there's probably people going, well, you haven't drawn me a circle yet. You've made some angles go around. But yeah, here's where the circle is. The circle is actually these coordinates here joined together. Imagine a circle with a radius of 1 going all the way around. I'm trying to keep the corner on the dot. I'm not exactly succeeding at that. Anyway, you can sort of imagine that. And that actually kind of summarizes what we did on page 7. On page 8, we started looking at this triangle here. What about a 30-degree angle, right? The other triangle that you get in your geometry set is your 30-degree, 60-degree, 90-degree triangle. And that one, we found out, if we were to do a little bit of arithmetic on it, we can make that triangle go right here. And by the way, I hope you're just watching. You don't have to draw anything right now. Don't worry. We'll draw this in our books in some of the pages coming up. Okay, anyway, this is, let's see, what is the coordinates of this point? Well, let's see. Well, if this is a 30-degree angle here, from there to there, that means that it has a height of 1/2 and a hypotenuse of 1. Again, the hypotenuse is always 1 all the way around this diagram. But this base length here is actually root 3 over 2. So that's kind of hard to see which numbers I mean where. So why don't we put the coordinates on it? That coordinate right there is x is root 3 over 2 and y is 1/2. So if that makes sense to you, go back to page 9 and let's fill in the notes. For a 30-degree angle, let's see, let's put this, can we see them both at the same time? There we go. Can everybody see here? I'll highlight it in blue. Can everybody see this triangle? Sorry, I'm freehanding that. Can everybody see this triangle in blue? All right, for this blue triangle, 30 degrees is this corner. The sine of 30 is opposite over hypotenuse, which is 1/2 divided by 1, which is 1/2. The cosine of this 30-degree angle is adjacent, which is this number here, over hypotenuse, which is root 3 over 2. And of course, tangent would be opposite over adjacent. And we could do a little bit of math on that. 1/2 divided by root 3 over 2. Remember, when you divide fractions, you times by the reciprocal, so it's actually going to be root 3. Now, it says on here that you should memorize this, and you should. You should memorize this, but I don't know about you. I'm not a great memorizer. I still don't know my own postal code most days. To me, it makes more sense if I can understand logically why This is root 3. That's root 3 over 2, and that's a half. And I understand it because I understand how these special triangles behave. Okay, anyway, one more set of triangles to put down. Oh, and of course, this 30 degree, I should say, can go this way. Let's do that. Let's put the other 30 degree triangles down. This will only take a minute. So about there, maybe. And up to there. Okay. I know that's not a great angle at the end, but it'll do. And the point here would be, okay, now take a look. If the coordinates there are root 3 over 2 and 1/2, then the coordinates here have to be, well, the x is negative, but the y is still positive because you're still going up. Okay, and that's now, how big is the angle from there to there? Well, if I went another 30 degrees, it'd be 180, so that's 150. Okay, so that's important to understand. The other two places I can put this triangle is I can put it here. So I'll put one that way. And there we go. So that would be a, okay, let's look at the coordinates now. Well, x is still the same, negative root 3 over 2. And y is now negative 1/2 because I'm going down in the y direction. And lastly, the last place I can put this 30 degree triangle is right here. And if you're wondering, well, why didn't you put it that way or something? Well, you can't do that because remember, we decided in the first lesson that the terminal arm has to be out here and the initial arm has to start measuring from the positive x-axis. So this is the only other place that the triangle can go. It's right here. And here, I'll just kind of continue going that way. And even though I know that's not the direction the triangle goes, I'm just trying to make a straight line for now. There we go. So there's the other place for this triangle to live. The 30 degree family, we call this. And again, its coordinates are going to be the same as these coordinates, except watch which one's positive and which one's negative. X is still positive here, but y is now negative because you're going down. And there we go. That's the 30 degree family. There's one more family to deal with. And you know, I had a red pen here. What did I do with it? I don't know what I did with it. Red pen, where'd you go? Okay, I've lost my red pen. I'll go back to pencil. The other family is the 60 degree family, and again, this is now the sort of the second part of page 8. Actually, it's the first part of page 8. I did the 30 degree family first. The second part of page 8 here is the 60 degree family, and the 60 degree family is the same triangle. I just flip it over. So now it looks like this. So now I make the triangle up here. So the triangle goes like this. And again, you're just watching. You don't have to draw this stuff. Don't worry. It's drawn. It'll be drawn for you in the next page. I'm just going to go through it once and then kind of talk about it. So this point here, now you're probably wondering, what do I do for the coordinate here? Well, notice it's the same triangle that this one was. I've just switched x and y because I've just started with the triangle this way and I've turned it over this way. It's the same triangle. So this is 1/2 comma root 3 over 2, and that's enough to help me fill out the rest of my chart. So this chart here tells me that looking at this triangle, and by this triangle I mean this guy right here, there's a 60 degree angle here, and what is the sine of that angle? It's the opposite over the hypotenuse. So the hypotenuse is still 1, but the opposite now is the y coordinate number, which is root 3 over 2. Does this look familiar? It's the same as the cosine was for 30. And look at the adjacent. The adjacent goes from here to here. And the adjacent goes from there to there. That's 1/2 divided by 1. And the tangent is opposite over adjacent, right? Which is, so let's see, hang on. Let's take a piece of scrap paper and do that. So the scrap paper tells me that, okay, so for my 60 degree angle, the tangent of 60 would be the opposite, which is root 3 over 2. Divided by the adjacent, which is 1/2, which is root 3 over 2 times 2 over 1, which is root 3. Oh, I just realized I goofed something up. I'm sorry. This is root 3. I'm sorry. You guys are probably like, oh, he's goofed that up. There we go. This is 1 over root 3. Again, let me prove that. For the 30 degree angle, sorry about that. I was thinking ahead there. For 30-degree angle, that's this triangle here, right? So opposite is 1/2. Yeah, that's, sorry about that. So let's show that. The tangent of 30 is opposite of 1/2, which is this height, divided by adjacent, which is √3/2. And as you can see, yeah, that's going to be 1/2 times 2/√3, which is 1/√3. Interesting enough, they don't usually rationalize the denominator on this number. You can write that as √3/3 if you want to, but usually they just write it as 1/√3. Okay, so that is the first part of the page 9 notes, and that there, I know you're probably looking at it going, well, that doesn't look like a unit circle yet. Well, let me finish it off a little bit. There's the first place I put the 60-degree angle. I can also put it up here. So that's going to go right up here and then straight down. And then, let's see, what coordinates does this have? Well, I know that this height is √3/2, so that's y. And this x number is 1/2, but it's in the negative direction because x is negative that way. Then I can put this triangle down here. And there we go. This point here is, it's got the same x value as the one above it, -1/2. And it's got a y value that's the same as this, but negative √3/2. And one more place I can put this triangle. I can put it right here. And that's going to, as you can see, just kind of continue this line. And it's going to give me that line. And that coordinate there is x is still +1/2, but y is -3/2. And if you look at all the points I've got here, maybe put a point up here at there, maybe put a point down here, maybe so there, and maybe put a point at this end. Okay, I kind of run out of room on that side of the page. Put a point over there, same deal, I kind of run out of room. But if you want, you can actually make yourself a nice unit circle by connecting these points. And again, that one's kind of off the page, back over. Sorry, this isn't the best circle I ever made. This one's kind of really ugly. But anyway, you get the idea. If you go around in a nice circle here, every time you, all the way around, oh geez, I froze. Too much hand movement. Sorry, there we go. As I'm go around this thing here, I'm making a circle with all these dots. This one, maybe I measured this one a little bit badly. But if I did this more accurately, I'd get a nice circle. In fact, if you look ahead a couple pages in your book, as we are going to in a minute, you'll see where all this comes from. But anyway, that's where that comes from. And okay, I can get this thing off the Kleenex box. I don't need such a big picture anymore. And give me a sec to get organized here. There we go. All right, focus. When dealing with these special triangles, we're easily able to determine the exact values. There's the chart with all the exact values. There's the diagrams where they come from. So now find the exact value of 225 degrees. So take a second and make yourself a sketch. Where's 225 degrees? Well, that's 180. Whoops, I'm off the page. That's 180 from there to there. So it's further than that. It's further in this way. 225 minus 180 is going to be 45 degrees. So it's actually 45 degrees from there to there, which means that it's this triangle here. Remember the triangle? It's √2/2 for a height. It's √2/2 for a base, or better yet, it's the opposite and adjacent that are √2/2. So if I want to know which quadrant it's in, let's see, well, it's 1, 2, 3. So it's in quadrant 3, and its related angle, theta r, is 45 degrees. Okay. Next, what trigonometric ratio of that angle from memory? What sine will it have? Okay, so when it says what is the trigonometric ratio, we should probably say what are the trigonometric ratios, because you can do them all. The sine of 225 degrees, Again, how do I figure that out? I think back to the fact that, okay, in this direction that's a negative, and this is also a negative, right? Because I'm going in the x negative direction and the y negative direction. So sine is opposite over hypotenuse of 1. So the sine of 225 is negative root 2 over 2. The cosine of 225 is also negative root 2 over 2. And the tangent of 225 is opposite over hypotenuse, which is 1. Those negatives cancel for the tangent. So that's the kind of question they're going to expect you to be able to do. They're going to ask you to be able to look at the unit circle and figure out any one of the multiple places that my special triangles could be sitting all the way around a circle. Don't worry about that big picture. I'll make you a smaller one in a minute. Okay, so example 6. Find the exact value of the following trigonometric functions. I would actually recommend that you pause the video and try it for yourself, and then I'll get back to you in a minute. Okay, did you try them all? So where's 120 degrees? 120 degrees is here. So what do I know about over here? Well, first of all, sine of 120. What family is 120 in? Go back to your notes if you have to. If you go back to your notes, 120, that's in the 60, that's in the 60 degree family. So that's going to have the same coordinates as the sine of 60 did. But in this quadrant here, y is positive, so it is square root of 3 over 2. I know what you're thinking. You're thinking, well, wait a minute, what about the hypotenuse? But the hypotenuse is 1, so just dividing by 1 doesn't change anything. 210, what family is 210 in? Well, 210 is 30 degrees more than 180, so it's in the 30 degree family. So what's the cosine of 30 degrees? Root 3 over 2. But where's 210 degrees? That's 180, that's 2. It's over here, right? So it'd be 30 degrees that way. Aha! X's, the adjacent values, are negative here. So this is going to be negative root 3 over 2. Okay. Now, you're not allowed a calculator in these, but when you're doing your homework, if you want to use a calculator to check what you're doing, you can. You just have to learn that square root of 3 divided by 2 is actually 0.866. So if you go the sine of 120, you should get 0.866. And if you go the cosine of 210, let me move it over that way. If you go the cosine of 210, you should get negative. Notice the negative on there, 0.866. So cool. All right, tangent of 330, that's 30 degrees. So that's in the 30 degree family because it's 30 degrees away from being 360. So it's 30 degrees from 360, so that's my 1 over root 3 number. But what do I know about tangent over here? Well, tangent is opposite over adjacent, which is, oh, sorry, I'm off the screen. It's opposite over adjacent, and this number here is negative. That number is positive, so it's going to be a negative 1 over root 3. Okay? Sine of 315 degrees. Okay, what's 315 degrees? That would be, let's see, what's 360 minus 315? That's going to be 45 degrees. So it's in the 45 family. So the sines in the 45 degree family are root 2 over 2. But is it positive or negative? Well, let's see. 315 is over here. Y is negative, X is positive. So opposite divided by adjacent should be negative root 2 over 2. And sorry, I'm off the screen again. And once again, if you actually know that the decimal representation of that, the decimal estimation of that is 0.707, if you go sine of 315, you're going to get negative 0.707. And yep, there's a negative on that. Okay. Next, the cosine of 45. Well, that one's actually where we think it is, so that one's easy. That's just root 2 over 2. That's right. When you're in quadrant 1, you are your own reference angle. 240 though, well, let's see, what's 240 minus 180? The reason I'm minusing 180 is because I didn't make it all the way to 270. So I know I'm in quadrant 1, 2, 3. So in quadrant 3, 240 minus 180, use a calculator if you had to, but that's 60 degrees. So I'm in the 60 degree family, and tangent of 60 is root 3. But in 240 degrees, let's see, I'm down here, and opposite, there I am again off the screen. I'm down here. Opposite over adjacent. Well, that's a negative and that's a positive. A negative divided by a positive is negative, so it's negative root 3. And again, you can check that. What is root of 3? Oh, it's 0.173. What's the tangent of 240? Oh, it's 1.73. And again, oh, wait a minute, I have this wrong. Oh, sorry, look at that. I've made a mistake. Some of you probably caught it as I made it. That's a negative x direction, isn't it? So what's a negative divided by a negative? That should have been a positive. Sorry about that. In too big a hurry, and I goofed that up. All right. So if you tried those on your own, did you get them? Those are the kinds of questions we expect you to be able to do without your calculator. So there's a whole bunch in the homework that you can try to kind of get used to it. I think what we should do now is we should think about relating back to Pythagoras. The unit circle is a circle with a radius of 1 centered at the origin. So it's got a radius here of 1 and it's centered at the origin. We call that distance there theta. That angle is theta. And what we then say is that the function of theta is that it has an x-coordinate and a y-coordinate. And the x-coordinate is the distance for this line. From here to here is the x-coordinate. From here to here is the y-coordinate. And what you actually do know is you know Pythagoras, right? You know that if this is true, that this is x, this is y, and this is 1, you know that x squared plus y squared is equal to 1 squared, which is just 1. So x squared plus y squared is equal to 1. And you can say that any point on the unit circle, which can be written as p, I guess I should have made this p instead of f. They use p. Doesn't matter. P. Any point in the unit circle can be written as p of theta is xy, and it can be found using trig. Notice that this number is this distance, but it's also the cosine of theta. This number is how high this line is, but it's also the sine of theta. How come this one line represents cosine when I was told that cosine is adjacent over hypotenuse? Well, remember, if the hypotenuse is 1, anything divided by 1 is itself. So as long as you have a unit circle where I call the radius 1, the x and y coordinates are the cosine and sine values for the angle that make this point. So let's put that into the notes. X is the cosine of theta, and y is the opposite side, which is the sine of theta. So for example, determine the coordinates of a terminal point on the unit circle for an angle of 240 degrees. Okay, so p of theta is equal to cos theta and sine theta. So let's find those. So that's the x and y coordinates right there. So 240 degrees. Let's see, where's 240 degrees on here? Well, 240 would be 60 more than 80. So let's see. Well, let's use our fancy fancy triangle from our geometry set. It looks like it's right there, right? 60 degrees there to there. So it's that point right there. And let's see, we'll do this. And we'll make a straight up and down. So there we go. So there's 240 degrees from there to there, but my reference angle is 60. And if that's a 60 degree right triangle, then this coordinate here has to be what? So think back to what we just did. Think back, if you want to say this page here. What do you know? Oh, this is the one where I didn't fix it yet. That's 1, that's 1/2, that's root 3 over 2. So for a 60 degree angle, the long leg is root 3 over 2, and the short leg's a 1/2. So the short leg here is a 1/2, the long leg is root 3 over 2, but both of those numbers are negative because I'm in the quadrant where x is negative and y is negative. So this coordinate is negative 1/2, negative root 3 over 2. Sweet. So from there, if that makes sense to you, you're going to then say that this is my cosine, this is my sine. So I actually have the point negative 1/2, sorry, I'm off the page, negative root 3 over 2. And that's what I was supposed to get. Okay. And just for fun, just to show you that this works, remember, x squared plus y squared should equal the hypotenuse squared, right? Pythagoras should work for this. And we know the hypotenuse is 1. Just to see if this works, just as a check, x squared add y squared should equal 1. Let's see if that's true. What is a negative squared? Well, it's positive. And what's a 1/2 of a 1/2? A quarter. What's the root of 3 times the root of 3? Well, it's 3. And what's 2 times 2? It's 4. and the negative cancels, and 1/4 plus 3/4 is definitely 1. Ta-da! So isn't that cool? This ties together coordinates, it ties together trig, it ties together triangles, circles, and Pythagoras. It's so cool when stuff in math all kind of comes together like that. All right, moving along. That was what page was that again? That was page 9 and 10. I'm going to try to do one more page, and one more page is one where I'm actually going to, again, just tie everything together. I told you don't bother drawing the circle that I was going to draw, that I drew on the big piece of paper. Here's one that fits on my screen, and check it out. I actually made little pictures for it here, little triangles. So check it out. If I were to put my 30, 60, 90 triangle right here, what do I know about the 30, 60, 90 triangle? Well, I know again that x is √3/2 and y is 1/2. So this is the coordinate √3/2 for x, 1/2 for y. Okay? Then I could take the same triangle and I could put it here. But now the 60-degree angle is here. This is the 1/2 side. This is the √3/2 side. So this has a coordinate of 1/2, comma, √3/2. And this is, of course, for, I'm going to put the angles here. This is a 30-degree angle. This is for a 60-degree angle. And then let's go around and finish the rest of it. So let's put the 30-degree triangle, or the 30-degree angle of the triangle right there. Okay, so what's the x coordinate? Now careful here, x is negative in this quadrant, so that's negative √3/2, positive 1/2. Let's put this here now for 60 degrees. So for the 60-degree reference angle, this is negative 1/2, negative √3/2. Now, this was 30 degrees. Right, so from there, if I had a terminal arm here, I won't mess up my diagram by putting a terminal arm there. But if I had a terminal arm here, that's a 30-degree angle. If I had a terminal arm there, that's a 60-degree angle. Well, if I have a terminal arm here, how big is the angle? Well, that's 30, 60, plus another 30, that's 90, plus another 30. Or think of it as 60 less than 180. This is the 120-degree spot. This is the 150-degree spot. Okay, let's keep going. Let's put the triangle here. Okay, here, actually, I made 4 of them. Would it help if I left all 4 of them sitting on the picture? You can see where they all kind of go. And if you're wondering, why is that the only 4 ways you can put these triangles? Because remember, we decided in lesson 1, or mathematicians thousands of years ago decided in lesson 1 there, that a terminal arm and an initial arm has to be kind of met as a requirement. So you have to start at the x-axis and end at the terminal arm. So 60, 120, or well, 120 would have been there. 150 to there. So keep going, what's to here? Well, it'd be 180 to this line plus another 30 degrees. This is 210 degrees. And what are the coordinates here? What's the coordinates at that point? Well, the x is negative √3/2. The y is negative 1/2. Okay. Here's the last of the 30-degree family over here. This is, if I were to go start there and go all the way around, oops, I moved it, all the way around and stop there, how many degrees have I cut through in this circle? Well, I'm 30 degrees shy of 360, so this is 330 degrees. And its coordinates are, x is √3/2, but the y coordinate is negative 1/2. Okay, so I'll slow down a little so you can get a chance to kind of put all that in. That's all of your 30-degree family. Now let's do the 60-degree family. I've already done that one. Now we can do this one. Sorry, that one got bent. And this one. And this one. All right, so we already did that one. That's 60 degrees, that's 120 degrees. What's this one? Well, this is 60 degrees past 180. So 180 plus 60 is 240 degrees. Now, what are the coordinates here? Well, again, the coordinates are the same as these coordinates. It's just, oh, sorry, I'm off the page. Maybe I should move up a little. There we go. So it's the same as these coordinates, but x is still negative, but y now is also negative. Wait a minute. Hang on. Why did I make this y negative? Can you fix that? Sorry about that. That's a, oops. Getting clumsy. There we go. That one should be a positive. These y numbers are positive. My bad. This y number is negative. This is the one I was thinking of. There we go. Sorry about that. So there we go. There's the x and y coordinates for 240 degrees. Okay, start here and go all the way around. So that's 180. 180 plus 60 is 240. 270. 270. This is 60 to more degrees, and I hit 360. So this is 300 degrees. Let me put the coordinates there. And this is 300 degrees. And for 300 degrees, this has an x coordinate of a half, be the same, x, but the y coordinate is the negative of that, negative root 3 over 2. Sweet. Okay, so that takes care of all my 30s and 60s. Let's go back to the other guys. What about my 45-degree angles? So I have a 45-degree triangle that can sit here. I have a 45-degree triangle that can sit there. I have a 45 triangle that can sit there. And I have a 45 triangle that can sit there. What coordinates do they all have? I'll do this one in pen. So that means no more mistakes. Kello, don't mess it up. So this is the coordinates. X is root 2 over 2. Y is root 2 over 2. And that's a 45-degree angle. Here, if I start there and go to there, that's 135 degrees. And this is x is negative root 2 over 2. Look at that, I goofed that up, that's a 2. And y is positive root 2 over 2. Okay, down here, this would be 45 past 180, which is 225 degrees. And the x coordinate and the y coordinate are both negative in this quadrant. And in this quadrant, if I start here and go all the way around, I am at the 315 degree mark. And the coordinates at that spot are x is positive root 2 over 2 because x is positive in that quadrant, and y is negative root 2 over 2. There. All the x's and y's are positive here. All the x's are negative but y's are positive here. X and y are both negative there. And here x's are positive, y's are negative. There, I think I did this right. Sorry, I made one mistake on it as I did it. We have something called the cast rule, which says that in quadrants 1, all three trig ratios are positive. And the letter A for all is A for cast. In quadrant 2, which is over here, maybe I should label the quadrants. This is 1, this is 2, this is 3, and this one over here is 4. So in quadrant 2, notice that any line that I make that is an adjacent is negative. So all the x values are negative, and x values are cosine values. So in quadrant 2, sine values are positive. Notice that cosine has to be negative, and then tangent has to be negative because tangent is always opposite over adjacent, which is positive over negative. In quadrant 3, only tangent values are positive, and it should make sense to you why that is, because opposite is negative, adjacent is negative. Negative divided by negative is a positive. So cosines and sines are all negative here, but tangent's positive. And then finally in quadrant 4, you can say that cosine values are positive. Sorry that this little box doesn't give you a little more room. There we go. And that should make sense. X values are positive, Y values are negative, so adjacents are positive. This is called the cast rule because you can make the word C-A-S-T. And if you're wondering what do you mean by C-A-S-T, well, C cosines are all positive in this quadrant. All three are positive in this quadrant. Sine is positive in this quadrant. Tangent is positive in this quadrant. So we call that the cast rule. All right, this is your first grown-up nice unit circle. I'm going to add one more thing to it. I'm going to add 4 more things to it. what is this point right here? Well, that's the point x is 1, y is 0. And this is, of course, for 0 degrees. And if I went all the way around, like all the way around once, that's 360 degrees. This would be the 90-degree spot. And what's the coordinates of that? Well, that'd be x is 0, y is 1. And what about this spot here? Well, let's see. That's the coordinates -1, 0. But it's also the 180-degree spot. And this down here is the 270-degree spot. And it has coordinates of 0, -1. And that takes us to the last page we're going to do in this video. Thanks for sticking around so long. The 90-degree family. So the 90-degree family works like this. This family consists of all of what we call the intercepts. So that means the x and y intercepts on the unit circle, and that would include the 90-degree mark, the 180-degree mark, the 270-degree mark, and the 360-degree mark. So looking at my unit circle that I just drew on the previous page, let me get these out of the way. Suppose we ask the question that it asked us, what is the sine of 270 degrees? So 270 degrees has a y coordinate of -1. Okay? Why is it -1? Because remember, sine is equal to this y coordinate. Okay? What's the tangent of 90? Okay, let's take a look. What's the tangent of 90? 90 is, tangent is opposite over adjacent, which is y over x. So hang on, the tangent of 90 is 1 over 0. Hang on. 1 over 0, aka y over x. What do we know about that? Never take your calculator and try going 1 divided by 0. What happens to you? It says error 2. Let's see if that's true if I do say, what's the tangent of 90? Yep, error 2. You can't divide by 0. You also cannot find the tangent of a 90-degree angle. Think about why that is, and it'll hopefully make some sense to you. All right, let's take a look at the cosine of 180. At the 180 mark, the x value is -1. So that's -1. And tangent of 270. Okay, tangent again. So again, let's write, maybe I should write cosine of theta is equal to the x value, which is -1. And tangent is the opposite over the adjacent, which in this case is y over x. So the tangent of 270 is -1 over 0, which again doesn't exist. -1 divided by 0, which is undefined. I should call that undefinable. And there we go. All right, here is the chart, all nicely put out for you. You just have to kind of look at it and try to remember it. For undefined, they just put a little tick, meaning that it's undefined. One more thing I maybe should do before we call it a day, I know this video has been kind of long already, thanks for staying by, is we should talk about the fact that in trigonometry, degrees aren't the only way to measure angles. So we can say that 0 degrees is 0 radians. We can say that 90 degrees is pi divided by 2 radians. And if you're wondering, where does he get pi divided by 2? Radians are a way to measure around a circle based on its circumference. So if I start here and I go all the way around, I've made a circumference of 1. So that would be, remember that circumference is equal to 2 pi r. So if I have gone all the way around with a radius of 1, circumference is equal to 2 times pi times 1, which is just 2 pi. So all the way around is 2 pi, which means that from here to here is 1/4 of 2 pi, which is pi by 2. Okay? 30 degrees is a 1/6 of pi. 45 degrees is a 1/4 of pi, which makes sense. It's a half of that. And 60 degrees is a 1/3 of pi. And that's where we'll stop for now. Thanks for watching this whole big long video. We'll talk to you in class. See you later.